The third option is this Hess's law thing. And Hess's laws is what you use when you can't work out experimentally what the enthalpy change for a reaction is. And sometimes there's good reasons for doing that. One is, someone said, does the reaction have to be fast? Well, the reaction has to be fast enough that you don't sort of grow old and die before it's finished. Some reactions are slow enough that that would be the case, right? And so one example that we think we talk about is the reaction where graphite turns into diamond. That is a reaction that does happen, but it takes an extremely long time. So you can't put a bit of graphite in your calorimeter, put the thermometer in and sit back and watch and wait for it to happen, because it'll take about 14 million years, right? So you can't experimentally determine the enthalpy change for that. Another reason why you might not be able to do it is that when you mix thing A with thing B, it exploded and took half the building out, right? That would be a bad thing to try and measure experimentally. And so what you can do instead is you can use something like Hess's law to work out indirectly what the enthalpy change will be. So, in order to try and illustrate Hess's law, here is the South Island. Some of you will be new to the South Island, yes? Yay, the South Island. Imagine that you wanted to go from Dunedin to Christchurch, as you might want to do, because Christchurch is a great place. It's a bit wobbly, but other than that, it's a cool place. And imagine that you looked up on Google Maps or something, as you can do now, and you found out what the latitude of this is and the latitude of this is, and you could work out by difference how much further north Christchurch was from Dunedin. Yeah? So it's about 360 k's to drive, but it'll be a little bit less than that directly north. Right? Now, you could decide that you're going to take your car or whatever and you're going to go straight from there to there, and that would be a certain distance north. Or you could decide that you were going to go from Dunedin to Timaru and then cut into Geraldine and then go back out to Christchurch that way. Right? That would take longer, but it would still end up being the same distance north from where you started, as if you went directly. Yeah? Yes? Or you could go to Palmerston and then you could go through the pig route up into Central and then you could go up that way. That would be much longer, but you'd still be the same distance north at the end of the day as where you started. Or if you wanted to be really interesting, you could go through the Catlins, Invercargill, Tuatapere, Manapuri, Queenstown, Wanaka, Haast, all the way up through here. It's very nice. If you haven't done it, you should, especially this bit. This is real nice up in here. And then all the way down again, right? That would take about 2 days. But you would still end up only the same distance north as where you started, right? So the point is that regardless of how you go from Dunedin to Christchurch, at the end of the day, how far north you've gone is always the same. At the end of the day. You see what I'm saying? Yeah? It's a bit silly, but you see what I'm saying. Hess's law is the same sort of idea, but for chemical reactions, and specifically for enthalpy changes in chemical reactions. What it says is that regardless of how you get from the reactants to the products, the overall enthalpy change will be the same. Okay? Regardless of how you get from reactants to the products, the difference in enthalpy between the reactants and the products, or the enthalpy change, will be the same. And so as we'll see, what it means is that imagine that you couldn't go directly from Dunedin to Christchurch because there was some tree down just outside of Temuka or something, and you had to do a detour. You could still work out how far north, how much further north Christchurch was from Dunedin, even if you couldn't go there directly, because you can go a roundabout way, and it's still going to get you back to the same distance north as when you got as by going directly. Yes? You know, I only just thought of that moment. I don't know how long I've been saying this lecture, but this idea of a tree blowing down, having to go a different way, that's just come to me. That's very good. I should remember that. So, consider the following reaction. NO2 gas plus solid carbon gives a half N2 and CO2. This reaction will be slow for all sorts of reasons that you probably don't really appreciate yet, but as someone who's been doing this for a while, I look at that and go, that reaction is not going to be a fast reaction. It's going to be a reaction that wants to go, but it's not going to go very fast. And so you can't put NO2 gas in a piece of coal in your calorimeter, put the top on with a thermometer and watch it, because it's not going to do anything, right? And so if you want to measure the enthalpy change, we have to do that indirectly. And so what we could do is this. let's imagine dividing this reaction into two steps. Two different chemical reactions which together will get us from our reactants to our products. So here's step one. NO2 gas goes to a half N2 gas plus O2 gas. Right? You might go, well, what's that got to do with anything? It doesn't matter for the moment, yeah? And let's imagine that for this reaction we can measure the enthalpy change, and we're going to call that delta H1. And then imagine we have a second reaction that looks like this. O2 gas plus carbon gives CO2 gas. Right? Now this one you kind of know works. This is just taking a piece of coal and burning it. Right? You do this all the time, that's fine. So let's imagine we can measure the enthalpy change for that, and we're going to call that delta H2. Now I should hasten to point out, we will always give you the equations that you can then combine to get the one you want. Right? We're never going to give you this and say work out some equations that you can then combine back together. Right? You're not going to have to do that. That's way too hard. I can't do that. You look them up in books. Yeah. Okay, so we're given these two other equations, step 1 and step 2. Sorry. So here it is again, and here are the numbers, the actual numbers now. So you can look this up. Delta H1 is negative 34 kilojoules per mole for the first one, and it's negative 394 kilojoules per mole for the second one. Now what we can do is this. We can take these two equations and we can add them together. And the way that we do that is, and again, this is about doing the working all nice, I would write them out like this, one above the other, then draw a line, and then you write the two equations added together. And so that's just a matter of writing down on the left-hand side this reactant and this reactant and this reactant, and then put the arrow, and then on the other side put down all the products, this product, this product, this product. Just write them out. Okay, so we're just adding those two equations together. And what we then do is we look to see whether there's anything on the left-hand side of our new equation that's the same as something on the right-hand side. And if there is, we can cancel those out, right? So if you look here, there's an NO2 gas here, there's no NO2 gas on this side, so that one can stay. But here there's an O2 gas, and over here there's an O2 gas as well. So that has no place in the reaction because this is just O2 turning into O2. There's no chemical reaction there, so we don't have to have it in our equation. So we can cancel these ones out, right? Everything else, it turns out, can stay, but these two cancel out. And so we can do that, like that, and then we write out our new equation, which looks like this, what's left. And so now what we're left with is this, and this, of course, is the equation that we started off wanting to know about, magically. Right? NO2 gas and carbon gives a half N2 and CO2. So what Hess's law says is that if this equation plus this equation gives this, then this number plus this number must give the enthalpy change for this equation. Right? Hess's law says it doesn't matter how you get from the reactants to the products, however you do it, the enthalpy change overall will be the same as going directly. So here we're going from NO2 and O2 to these things in two steps, sorry, NO2 and carbon to the products in two steps. But that's okay because it adds up to give the same overall equation, and so the number that you get should just be the sum of those two numbers. And that should be the enthalpy change for that overall reaction. And so this is how we might present the third way of asking you to work out an enthalpy change in a question. We would say, what's the enthalpy change for this reaction? And then we would give you 2 or 3 other chemical equations which each had their enthalpy changes with them. And if you see those other equations, you go, I'm supposed to do Hess's law. I'm supposed to combine these equations together somehow to get the overall equation and then add up the numbers the same way to get the enthalpy change that I'm after. Now let's look at this diamond to graphite reaction. So we can't experimentally determine the enthalpy change for this. because it's too slow, right? And probably you want to keep your diamond for something else anyway. But what we can do is this. We could take our diamond, and people have done this, and you burn your diamond to make CO2, right? So you get out a blowtorch and you just burn it, and you measure the enthalpy change for that reaction somehow, right? And so you can write an equation like this. Carbon in the form of diamond plus O2 gas gives CO2, and delta H for that is negative 395.4 kilojoules per mole. And then we could do the same thing with our piece of coal, which is basically just graphite, right? So carbon in the form of graphite, we're all happy that diamond and graphite is the same stuff chemically, yeah? It's all just carbon. Yeah? So carbon in the form of graphite reacting with oxygen gas to give CO2, the enthalpy change for that is negative 393.5 kilojoules per mole. So they're slightly different because diamond is different to graphite, yeah? Now if we want to use Hess's law to work out the enthalpy change for carbon in the form of diamond turning into carbon in the form of graphite, then we can't just add those two equations together as they stand, can we? Because then we're going to have something that looks like carbon diamond plus O2 plus carbon graphite plus O2 gives two CO2s. They're not going to add up to give the overall equation that we want, which is carbon as diamond goes to carbon as graphite. And so in this case we have to manipulate these equations that we're given a little bit before we add them together. So what we do, and to an extent you just have to kind of look at the equations and work out what to do. There are some tricks, and because we've done this now and you do this in the tutorials, the guys will hopefully give you some insight into the tricks. But in this case, we just hopefully by looking at it, you can see what you have to do. What we do is we take the second reaction and we turn it round. So instead of being carbon as graphite plus O2 gives CO2 gas, we make it CO2 gas goes to carbon as graphite plus O2. The reverse reaction. If we turn that equation around, then obviously this is going to have to change as well. And if we just flip it round, all we have to do, it turns out, is change the sign on that number. So instead of it being negative 393.5, it becomes positive 393.5. Yeah? And so if we do that then, here's our first equation, just as it was up there, with delta H is negative 395.4, and now here's our one that we flip round. So now it's CO2 gas goes to C graphite plus O2 gas, and our number now is positive 393.5. Yeah? We can then add those together, writing out all the reactants from both equations on the left, and then an arrow, and then all the products of the two equations on the right. And then we can go in and see what things appear on both sides of the arrow, which we can then cancel out. And in this case, there's lots we can cancel out. We can cancel out the CO2s on both sides and the O2s on both sides. And what we're left with is the thing that we want. C as diamond going to C as graphite. And so because by manipulating that second equation the way that we did, that enables us to add these two equations together to get the equation that we want, that means that we can now add together these two numbers. The original number for the first equation plus the new number for the second equation, add those together, and that will give us the number that we want, our enthalpy change for that reaction. So there's two things you can do. Well, there's three things you can do. You can either just add all the equations together and it works and you're happy. Or you can take one of the equations, or maybe more than one if there's like three equations, take one of the equations and flip it round. If you do that, then you have to change the sign on the value for delta H that goes with that equation. Right? And so you would do that if, like in the case here, that means that when you add the equations together they add up the way you want them to. And the third thing you can do is you can take one of the equations and you can multiply it through by some number. You can say double everything or halve everything. Again, you would do that if that meant that when you added everything up, it added it up to the equation that you wanted. If you double everything in the equation, then you have to double the number. If you halve everything in the equation, then you have to halve the number that goes with it. Yeah? And so using those two tricks, you should be able to take any set of equations we give you and then work out how to fiddle around with them so that you can add them up to the overall equation that you want.